high performance computing course. Um, it's online through Flow. Um, uh, and I have in mind that we might have meetings every week, just like this one. Just make it a recurring meeting. Um, so yeah, welcome to the course. This course lasts until May 31st. Um, and it's going to be mostly on the weekends. We have a volunteer, Anurag, who's going to be presenting the first lecture. So I'll hand it over to him.
Yeah, I think Anurag is joining us again. Hi, this is Harshit. I'm facilitating the background so this class can work, function well. Anurag is joining us again. I think he is facing some problems regarding audio or video settings. Uh, we're gonna wait for a minute until he rejoins and should be able to take it forward. By the way, welcome Arun, welcome. I don't know the name in the class. So Lareen, until let's say Anurag
Okay. Hi, everyone.
joined us. Okay,
Um,
perfect, perfect.
Hi. Good to see you. So I would just say I'm going to hand it over to you to present. You have the slides, right?
yeah, I have the slides with me.
Okay, good. So feel free to share your screen and run through the slides.
Yeah, sure. Mm, sorry, I have just a lot of things open on my laptop, so I'm browsing there. Um, yeah, this one. Okay. Is it visible?
Yeah, I can see this.
Okay, awesome. Uh, okay. Hi, everyone. I am Anurag. I think I skipped some previous part of the introduction. So, yeah, I will be driving this lecture on a very brief introduction about the course, where we will deep dive into the basics of parallel processing and why do we need parallel processing. So the first slide is so starting here, we first begin with um, sorry, wait, it's lagging for me a bit. Okay, so it's we start with Howard Enkin um, observation where he mentioned that most of the problems that we try to solve are unsolvable because we don't have the means to solve them right now. Maybe we don't have the mechanical computation to solve those problems. This statement was made in 1937. Now we are in 2025 almost, so we have seen how we have evolved as a species where we can just tap anything and do most of the problems with um, the modern AI revolution coming in, where this statement is more or less false. So this is a picture of um, how a physics problem was simulated through a computer. These many people were required, such a large scale was required to do a very simple physics problem when we see it in today's dynamics. So, with starting with these statements, let's deep dive into what we have in the course. So, we will go through what is in this course, what is computational science, what is data science, and why do we need parallel processing as we advance as a species, and what are the challenges for uh, when we are doing some problems of parallel processing. So computational science is something that requires much more compute, much more system flops, and much more uh, processing power. Data science requires us like more data oriented problem statements where we require to store and compute over a lot of large data. And we will see how the problem statements and how large scale of these problem statements could be, that would require us to use parallel processing. um, so till here we are cool, right? Yeah, I hope like everyone is cool. Yep, I assume everyone's cool. So first we will see what exactly is in computational science. So computational science is basically integrate of science and engineering, modern computer architecture, and applied mathematical models. So we first need a problem statement to solve and to see it from a science perspective, where we are able to make it into complex equations. That is where we need science and engineering. We need applied mathematics to make a concrete problem statement or equation out of them. And once we have the complex equation ready with us, we would require the compute power to do more analysis on top of it. So ideally, how system goes is we create a theory first using our sciences, using the science, and then we have to experiments to conduct to see whether our theory is correct or not. To conduct these experiments we require modern computers, because these experiments could be very high data intensive or very high compute intensive when we see them. So seeing a sample case, let's say we want to find what would be the weather tomorrow, it's very easy to search on Google. But how it has developed over the years is Google also accumulates a lot of climate based data based on the geographical location, the latest weather data, the um, data related to the cyclones or the recent currents, etc., what's happening in the surroundings. And based on this theory, they have conducted a lot of experiments to have precision models developed that could articulate how the weather would be tomorrow. And they use to articulate these things better, they have a lot of compute on their end to do this part. So most of the times we cannot do these experiments. So we have a theory, we need to experiment it, but those experiments might be too slow. Let's say we want to see the climate evolution. So climate evolution happens across years. It requires 50 years to 100 years um, to see the climatic change that is happening, and we don't have that much time span in our lives to see how the climate has changed. And sometimes it could be too dangerous, such as drug discovery, where we want to test out new drugs. We had in the case of COVID, where we were testing new vaccines. So we cannot just directly test them on people and let them die. We need to first test them. We first need to have some simulation where we can test them and find out the low hanging fruits or low hanging irregularities that we can solve on the fly, where we can do much more iterations very fast, so that we know where are the gaps in our theory, and we can modulate our theory and conduct better experiments when we have to. Or sometimes the systems could be too complex, where, let's say, the case of drug discovery itself, let's say we are uh, discovering a drug to cure lung cancer, but it can impact somehow our intestines as well. So those are the complexities that could arise in conducting an actual experiments. And that is where computational science relies more on how can we simulate these. And simulations is not just related to science, it is related to the modern industry where I come from, where we develop a lot of products. So how we generally do is we do designs on paper or in documents, and then we do a very quick prototype. And once we have a prototype ready, we kind of test it out across multiple partners and see whether does it work good for them or not. But sometimes the problem statement could be very hard, where we cannot even create prototype. It could be too difficult. Let's say we want to create a wind tunnel to test the of uh, aerodynamics of a plane. So something like this is very difficult to develop, and also something like this is very expensive to develop just for the prototype and to the sake of throw it away in near future. Sometimes when we are prototyping, so let's say we are prototyping a weapon, it could be too dangerous to create a weapon which does not function properly. Can it injure someone, or can it be harmful to others? So in such cases, we rely mostly on simulations. And to have better simulations, we need a much more um better computational power. So in going slides, we will discuss this further. Please let me know if I'm like going too fast or going too slow, or um, any comments on till now, or any questions till now. Okay, cool. I will proceed. I am audible, right? Yeah. Okay. Awesome. So let's take a like how we actually kind of describe a problem statement as a part of computational problem. So let's say we want to build an um, aircraft. So first we need to understand what exactly are the scientific and engineering terms that are involved in creating an aircraft. So first it will be understanding aerodynamics, understanding fluids, how they work, understanding viscosity, um, how does the pressure work, how does the humidity work, how does the materials interact with air, and how weight, etc., interact with the environment. What are the dynamics of a thing that is flying? So once we have the science regarding it, then we have the equations regarding it, and we have a mathematical modeling regarding this one. So similar, so we have like Stokes equation in fluid dynamics, where we this partial differential equation, where we see how does the aerodynamically actually works. This is mostly conservation of mass and momentum when we think about it. Once we have the mathematical modeling ready, it is not always 100% accurate for us to uh, solve that mathematical modeling. We sometimes do some approximations so that we can reduce the number of computations that are required to solve that problem. And we do some kind of approximation just for the sake of our convenience, and faster results may not be 100% accurate, but to some sense accurate. And once we have the equations ready on how we can fly an instrument, we simulate our environment, where we test, okay, if we have this pressure to this material, does it actually fly? We have the gravitation constants, we have the wind constants ready with us, and we can simulate in multiple environments with high wind, low pressure areas, and also high fog. How does it interact with the systems? And once we have the simulation done, we collect all these results and we analyze, did we perform, did our results align with what our theory is? And we also try to verify whether our indexes or the tests that we have created to analyze them, are they fundamentally correct or not? um, so yeah, this is how we see, we try to break down a problem statement into a computational science problem statement, and try to articulate it as a simulation. So in so what does computation why does computational science actually need like performance? So um, we in coming slides we will see an example where we will see how difficult it could be to actually articulate a system and how many different variables it could require to solve a problem statement, and that is where our performance requirement actually comes in. So we sometimes in cases we want to have lower execution time. Let's say a geographical area 1,000 kilometer to us is hit by a cyclone. We want to see what impact does it have on us. So in such scenarios, we require the simulations to run in lower execution time. So we need much better performance. Similarly, we would require a higher accuracy, where we would be required to have more accurate data and rather than just approximations. And we will have complex models. We will one if we are trying to find out what impact the cyclone will have, we also need to know what is the current weather looking like, what is our geographical latitude, longitude, and altitude of the area that we are actually living in. So the more variables we try to incorporate in our equation, the complex the model becomes. And for more variables, more interactions with each other, we would require even more computational power to solve that problem statements. And that is where we come to high performance computing or big compute problem statement. So in the modern era where we are trying to simulate and solve much more high computation involved problems, uh, we require big compute going forward. And so we discuss try to see this in this example where we actually try to find the weather or navigate the weather. So we are so to find to simulate a climate of an area, let's take a hypothetical situation where we are trying to create some um, differential equations, and we are trying to discretize the an area to calculate its climate. So we have like latitude, longitude, and altitude. We have created a basically a voxel, and every voxel at a delta t time, we are trying to estimate what would be its climate looking like. And we also have several other variables which account for the climate, which are previous climate, how does it look like, we have temperature, we have humidity, and then we have current weather as well. So these are the different variables that account for this equation. And if we try to see it more onto the computation side, we will even find it much more um, much more data intensive, where we have not data intensive but compute intensive rather. So let's take a geographical area of 10 to the power 4 in length, 10 to the power 4 kilometers in width, and 10 to the power 4 10 kilometers in altitude. So taking this very small geographical area, and we divide this area into multiple cells of 1 into 1 into 1 kilometer cube. So we have each cube and each cell, we have to record the climate at a delta t time, let's say 1 minute. So we want to find out what would the climate of each voxel here at a specific 1 minute time limit here. And let's say we have only 50 bytes of data that we require to create such voxel. So for 10 to the power 9 cells that we have here, it will be around like 50 GB of data, which is a huge data. And let's say we require 10 to the power 3 flops or 10 to the power 3 um, instruction executions. So to like just estimate the climate at a given timestamp, it will be requiring around 10 to the power 12 flops or 1 teraflops. And if we want to do it for a day, this is for a minute. And if we want to do it for a day has 1440 um, minutes, so it will be nearly 1440 teraflops. And if we have 100 g flops, processor, then it would approximately take 4 hours just to create this simulation environment. And mind, we have not introduced any pressure, temperature, humidity, wind speed, etc. variables. So even just to create such a basic simulation environment, we require so much data and so much time. So um, s- so that's where we are coming towards, why do we need performance. So let like we have discussed in previously, we are um, in the need of the hour, where we want to create this simulation very fast. We want to see whether the cyclone that has affected that area, can it affect us as well. So we are time critical, we want more compute and much faster compute to not take 4 hours, maybe do this same computation in 30 minutes. We want more accurate results, we want to tell people whether to evacuate or not. So that's why we need, let's say, even more granular data, let's say 10 to the power 10 cells instead of 10 to the power 9 cells here. And let's and as discussed, we have not taken any of these climate functions yet into account for creating this equation. So yeah, if we try to introduce these variables as well, the um, problem statement will increase even further. So to see it from the time perspective, this is a time scale from this is a log time scale. This is the performance and number of operations. So we have kiloflops, megaflops, and similarly till yotaflops, 10 to the power 24. So our problem statement required around 10 to the power 12 flop into 1 day prediction. This is nearly 1000 to 10 to the power 15 flops. And let's take the processor has 100 gigaflop frequency. So it would require around 10 to the power 4, or the time that we have estimated around like 4 hours to just compute this very small climate simulation. And if we see actual problem statement like Gaussian elimination, which is very basic matrix inverse matrix computation, it requires around 10 to the power 22 operations to happen. And if we don't have sufficient compute power, then uh, we can definitely say that even trying to solve small problems can become intrinsically problematic, because we don't have the sufficient compute power. Let's say we have 10 to the power 6 flops only, then um, we cannot compute them with that specific performance, or with that specific uh, performance processor. So yeah, this is still computational science. If we want to like discuss some parts, I can take a pause here, and then we will deep dive. Then I will give a brief on how what exactly data science looks like. um, I think I'm going too fast. Hmm.
I think you're fine. So I just wanted to add that for the PDEs, PDE means partial differential equation. As you were talking about before. Yeah, right here this slide. So regarding mathematical modeling, this is very common in chemical engineering when you're modeling a chemical reaction. So what happens when you mix the reactants is you have to heat it up to a certain temperature, and then um you the reactants form a product, but how much of the product it forms and how much heat it produces also affects how quickly the chemical reaction happens. And it's really hard to model a chemical reaction using traditional methods, um, because there are just so many variables, like the temperature changes things, and then the amount of reactants and products also changes things. So one very common technique to model this is through Runge Kutta. uh So Runge-Kutta is a way to solve partial differential equations, and this thus solves like how the chemical reaction takes place step by step. We're going to learn it later in this course.
So okay, so I think I did not give brief about myself. So I am an engineer who, so data science is somewhat I come with a background with as a working professional. So I work on mostly like data collection part, on how we can collect good quality data and how we can refine it for data science teams. So I come from that perspective. So this part is a bit close to me. So data science is a field where we are um, integrating three domains, where we have computer science, where we have statistics, and we have the domain specific data that we require to solve that specific problem. So let's say we want to see whether how many um, let's say we want to see how exactly or what is the number of increasing deaths due to lung cancer. So we have the data of uh, how many deaths occurred in a specific year. We have the computation power, but we don't have the domain specifications, where we don't know how to identify how do we identify a cancer patient. So that becomes kind of senseless data. So we need the domain specific knowledge to exactly see what is exactly happening in the data, and data insights give a lot of details about how the problem statement looks like. And most businesses today and even cricket today is driven by database decisions. So the data processes are more or less same across different companies, where we have a data collection and cleaning pipeline. We collect a lot of data from different sources, and then we have this humongous data where we try to process them. We try to massage that data and create some ETLs on top of them to put that data in some data warehouse or data lakes, and that data is available for the data science team to interact with, and or business users to see some reporting on top of it. And so we have a data integration and analysis here, where these data pipelines are created, and where the statistical learning, where the data science team actually uses this data to create some models and takes some business decisions based on them. So like how we have grown as a um, data intensive species, where I don't think like anyone here would not have any data footprint. Like it's completely impossible in today's world to not have a data footprint in on internet. So everyone requires data, and this data could be very useful and could be humongous to compute on, to see what exactly is the underlying problem statement, or what we can improve on in our processes. So to give an example, in 2013 Google had around 10 exabyte of data. And Facebook had around 300 plus petabytes of data. And similarly, CERN large hadron collider had around like 600 MB, 600 million events, where each event was 1 MB, so around 160 petabyte per year. So similarly, in 2025, IDC expects around 175 zettabytes of data to be created for till now, and which is always increasing. And given given the AI era, where data creation, at least text data creation, is very easy, this data will increase drastically. Um, so, similar to what we have seen in computational science, data science also requires the same performance matrices, where we want to compute over large amount of data in lesser time with higher accuracy, and take much more convoluted data and create some mathematical models out of it, which is happening in current world of attention based LLMs and the AI era. So this is where big data actually empowers the data science to create pipelines and to create ETL pipelines to um, deliver high quality data to the data science team so that they can create much more sophisticated statistical model, and business teams so that they can take better decisions on how they should see and analyze the market. So yeah, as said, data is the future. So to uh, make um, any problem statement, any engineering problem statement, scientific engineering problem statement, we need both simulation based decision making and data based decision making. So uh, um, okay, I did not introduce myself. I'm an engineer in ad tech. So ad tech basically means how the advertisements happen across multiple platforms, Google, Facebook, for fanatics. So we see this. For every problem statement we have a simulation based decisions and data based decisions, and we need both of these decisions at simultaneously so that we can take better decisions. To give an example on this, so uh, once we were this was the scenario when I think Messi changed from Barcelona to PSG, and we had sudden spike over Barca products that were like going out of stock, specifically for Messi because they were the last limited stock. So simulation, so data-based decision could not have picked those things. It would be only simulation based, where we would have parameters about this, how a player actually changed his team, affected the market, can affect the market. So um, that would have alerted us that okay, this product can go out of stock very fast and we need more product of this kind. Similarly, database decisions help us analyze which, let's say, a player who is playing currently in any college and he's going to an actual season, or he's playing in IPL for Indian folks and is going to international cricket. So he has more chance, and he has a lot of fan following. So he has more chances of merchandise selling. So that is where database decisions would be useful. So both of them combining actually gives us a whole highlight of how a problem statement is, or how a product could be actually put forward to people. um, so we have multiple problem statements, uh, which could be data heavy, which could be highly coupled and would require high performance compute, or some could be data not that data intensive. They will require some amount of data, but they will be very less data intensive. And some could be loosely coupled problem statement, which means they will have lesser variables, but they will require high throughput computing. So something like metagenomics, where we are trying to find genome sequencing and see how did the genome develop over the multiple years. So the number of variables here itself is immensely large, and we require a lot of data and a lot of uh, um, genome sequences to see which genome sequences actually um, imply which genome sequences imply which trait exactly. So this is a data high performance and high data intensive task. Similarly, we have something as weather forecasting. We need for weather forecasting, not for climate forecasting. So weather is limited to like only a small time frame, where we are limiting to last 1 week to next 1 week of data. So we need to see how does that anomaly happen with some more variables, like um, from the climate data, how the recent climate or how this time frame climate looks like, and some data like is there a cyclone nearby, how the currents look like. So the data is less, but the number of variables becomes very large. So this requires a high performance computing and a slightly less data intensive job. And similarly, we have for image processing, where we have a lot of data or a lot of images that are required. Let's say we want to mask the images. So we have a lot of images that we need to compute on, but the images are separate data in themselves and they require high performance, but all the images could be done separately. They are not part of the same problem statement. So they require high throughput, but they might not require high performance or high single equation based solution. They could be handled separately. And similarly, we have a data light, and uh, similarly we have cases where we don't require that much data and which requires high throughput. So the need of parallel processing, like as we have seen that the scale of how big the simulation could be and how data intensive the jobs could be. So we know now that we require much more processing power. And as per Moore's law, it mentioned that the number of transistors would uh, double every 2 years. So based on the 1960 to 1965 graph, but so the number of transistors in a dense integrated circuit doubles approximately every 2 years. This is the exact statement. But as we have come forward, we have seen that this does not actually holds true, because with the increasing number of transistors that we have on the integrated circuits, the sheer amount of power that we require to uh, increase the compute becomes exponential becomes an exponential problem, where um, my I can have more compute, but I would require even more power to uh, power the systems to do increased performance. And it's not just a problem statement about power, it also becomes an important problem of thermodynamics, where we don't know how to handle that large uh, temperature of the chips, or how do we cool down those chips even faster so that the compute could be done better. Because modern computers, we cannot do them, but if they are stored somewhere in the warehouse systems, maybe we can monitor them. So um, this is where the case of parallel processing actually comes. So we can see over the years we have the frequency of the processors increasing, but they have reached an asymptote here where we cannot increase the frequency after a given limit. Similarly, we can see that we cannot increase the performance from a single thread. However, we have seen that we have been increasing the number of transistors on the chip throughout these years. So what we try to do over here is we are trying to increase the number of logical cores, or number of processors in a given CPU itself, so that we can distribute the same task or the instructions of the same task across multiple processors or multiple cores of the processor, so that that process could be broken down into chunks which could be solved by these cores and could be delivered independently by each one of them. So this was the challenges of parallel processing. So just when the computer era just started, people had different opinions on how computer would look like the chairman of IBM had there would there is a world market, maybe five for only five computers, because at that time the scale of a computer was huge, and it could not have been as easy as we have laptops today. And similarly, Bill Gates once said that 640 KB of memory would be enough for anybody, but I don't think uh, anyone can survive with this much memory in today's world. So as we have seen how the complex statements could be, how complex data could be, and how we cannot rely on just single processor machines. So that is where we need to rethink much more on how we design our software. We need to think on how the parallel processing in a single computer works. We also need to think how we can distribute um, the data across multiple servers or multiple computers to solve them. We also need to rethink our algorithms, where we have designed most of our algorithms on single threaded system, how we can upgrade them to use the full potential of parallel processing. And similarly, we need to design our tools, programming models to adapt the more parallel processing era. um, so uh, um, these are um, more course oriented slides, I guess, now, like what will be discussed in the course. So I think Harshad, you should take this one, or Lanning, you should take these slides if possible, like what we will discuss in this course exactly. um,
Yeah, so we're going to discuss all this. Um you can go through each slide. Uh
okay.
I think all this is relevant, yeah.
Yeah. So as a part of this course, we will see how parallel programming actually looks like. So if you think that programming is hard, parallel programming is going to be really hard. And first, we will see how uh, parallel programming actually we can scale from one processor to two processor. And once we have learned that, we will try to even scale it further. We are not limited to just 2 or 10 processors, maybe 100 processors or 1,000 processor in case of distributed performance, distributed computing. um, um, so I think this is very relevant to, this is specific to course C2005. So I will just skip this slide.
Yeah, so CS205 was CS205 was an old course number for this course. So they changed it to CS2050, but this is the same course. Like this is the same course that we're learning now, it's just a different course number. So you can go through this.
Okay. So uh, what we will see as a part of this course is how we can how to see a problem statement as a parallel processing problem statement. We want to see how we can design large scale systems to properly analyze these parallel processing statements. We will see some data architectures and some existing softwares like Spark, OpenMPI, etc., to see what are the existing standard industry level APIs or softwares that we use to have parallel compute and parallel data processing. And um, yeah, hope after this course we will be in a position to um, you apply those um, conventions that we have learned in our day-to-day projects that we try to do. And so these are the fundamentals that we will learn for parallel computing. We will start with parallel processing architectures, then on the cloud, then some aspects of cloud computing, because we want distributed networks, and creating a network of 100 PCs is not feasible. It is very easy to do it on the cloud, but not on prem, or in physically holding 10 computers is pretty difficult. And running software on 10 physical computers is even more difficult. Then we will see the application of parallelism and how we can design more algorithms and programs to run parallelly on these distributed softwares. For parallel computing, we will first learn the um, primitives of parallel computing, and then we will move toward performance optimization on how we can use our processors to maximum extent. For this, we will first learn basics of what existing processor look like and how we have developed to a better optimized processors. And then we will discuss some parts of accelerated computing, GPUs, OpenACC, etc. libraries that are currently driving the AI community on how these actually works. Then we will also see the shared memory architecture like we have for M1 and M2 chips, how they have surpassed the level of Intel chips. So how they utilize the shared memory to maximum extent in case of parallel processing. And then we will also see how we can have distributed memory where we have multiple systems existing and they are sharing memory for the same high computation task. And similarly, for data processing, we will first see what are the fundamentals that we require to see data processing. We will first start with batch data processing, where we will take like a huge amount of data and we divide it into multiple batches and learn some techniques on how we can um, do batch processing faster. We will go over Spark, Hadoop, or some uh, distributed data processing system for the same. And then we will also see stream data processing on, let's say, stream data processing is when we are seeing live stream data or uh, uh, yeah, live stream data or a whole data which is flowing in and computing on the fly. Let's say you are browsing on Netflix and the recommendations change based on how you browsed. So though they are analyzing your data in real time, almost real time as a stream, and they are computing the results on top of it. So yeah, we will discuss Spark, MapReduce, uh, MPI, message passing interface. No, this is MPI library. Then we will see OpenMP, OpenACC for GPU, uh, GPU running GPUs on the cloud platform mostly. And we will be using AWS. We will be partnering with AWS. I'm not sure on that. Harshit or
So
Logan?
for the AWS server, I haven't set it up yet, but I'm looking at the AWS free tier products, and I'm hoping to get us set up with a server.
Yeah. I think they have a free tier for students, but I'm not sure if they have for working
Hmm,
professionals.
I can look into that. I have a .edu email that I can still use,
Mhm.
so hopefully I can make an account before I lose access to it.
Yeah, yeah, I will also look into that one. Um, then we, yeah, as said, we don't have enough resources to run on-prem servers and do our own 100 computer computing. So as prerequisite of this course, we will all need like basics of C, a little bit of C++ as well, because we will be diving into OpenACC and OpenMP, which are C++ libraries, and some parts of Python, and some basics of Linux, like how Linux file system actually works, how the kernel works, how does system actually invoke kernel calls, and how to use command line interface, some basic understanding of algorithms, some basic data structures, stack, queues, trees, heaps, etc. And we will be learning new programming models and platforms as well, on how to run multiple instances on cloud platforms. And it will be like challenging as well as somewhat time consuming, so all the best. And yeah, I think like these slides I can just skip because this is how
Yeah,
I don't think we will be graded, hopefully.
yeah, you can skip those.
Yeah. Yes.
but we're going to have hands-on assignments and labs later.
Mhm. So I think these folks are missing from today's call. And yeah, okay.
Yeah, so this week I'm gonna try to get us set up with an AWS server. Hopefully looking into the free tier, and I'll contact you all later. Harshit, do you want to make a poll asking everyone's time zone and if this is a good time for people to meet?
Yeah, thanks, Lorene and Anurag. I think this was a great session. And for the next session next week for the lecture A2, as Anurag brilliantly volunteered for this lecture, and this is exactly what we are supposed to do. And so, a great round of applause, maybe silent applauses for those who are missing. But I think, this was amazing. And for the next week, we would be calling up another volunteer. So, anyone over here would like to be a volunteer for the next lecture A2, just let me know or DM me. You can also let me know later, before the second week or like in the coming days. And regarding the time zone, since we are placed in different parts of the world, Lorraine is in the US, many of us are in the Indian time zones, and hopefully there are other people as well. So we'll choose a time that best suits to, if there is any time zone preference, you can add over here in the comments, or we can have a poll as well. So feel free to add in the comments, or we can choose a time. And Arun or Rubayat, if you would like to volunteer for the next week, feel free. Every how this works is every week this is a peer learning exercise event on a hard course, and everybody, we are adopting a methodology of learning to teach and teaching to learn. So feel free. We will be able to get to spend each lecture every week. So, and we will need, we highly recommend, we will need motivated people who could be volunteer for that, just like what Anurag did this session. So I hope, Lorraine, this is good, or if there's anything else, let me know. As usual, we are using this flow platform. So I will onboard you with, creating the event and the link. Just you need to reply to the onward course email where to volunteer for the next weeks or the topics on the coming weeks. Feel free.
Okay, thank you, Harshit, and also Anurag, you did an excellent job today.
Yeah, anytime. I will try to take like one more session when we actually reach the data side of it, where I will try to discuss some of the problem statements that we actually encounter in day-to-day life. So, like most of the times it happens is what data science team gives us, hey, we want this report and we want it for 2 years of 2 years delta from now. So we want 2 year history data and we want it by end of 2 weeks so that we can create some models and test them out. And we do so many data processing on top of it, and in the end they say, oh, this data was almost useless, and maybe we require some more data or newer models to see, or more a better data to analyze this problem statement. So yeah, I will take actual problem statement and try to cover that part as part
Yeah,
of this course.
thank you, Anurag.
Yeah, awesome.
I think I have one last question, or if we have time for a couple of questions on this Q&A. So, to anyone, Lareen, Anurag, or anyone present, Rubai, Tarun. So on the slide there was mentioned a term IaaS, like infrastructure as a service, right? The challenges, or one of the, let's say, paradigms towards parallel computing. So, as could you explain me the difference on the different terminologies used, like SaaS, PaaS, infra as a service, just like a small brief around how they are substantially differentiated?
Oh, that's a question to me.
Yeah, anyone.
Okay. So software as a service is basically, let's say, uh, you are, let's say, WhatsApp. Someone is building a WhatsApp network for me or WhatsApp selling platform for me. So that is a software I am giving as a service to which I can pay some amount or my personal data so that they can use. Infrastructure as a service will mean actually something that my and software as a service does not require me to monitor what my software looks like, who is maintaining it, who is taking care of versioning it, and how frequently is it getting updated. If it crashes, it's not my responsibility. Someone else will help me out in that case. That is basically how software as a service works. Infrastructure as a service is basically I have the rights to the instance, the physical instance. I know that I want an instance, so I have created a request, and that instance somewhere in the service provider's data warehouse is sitting and is allocated specifically to me. It could be an instance, it could be some database which is running on some instance, or it could be just a block of memory in which I can run my program, a Lambda function, or it could be like a um, Docker block or like EBS system on which I can run my Docker or deploy my Docker. So I can take that instance on lease, and it costs me around like $2 or $3 per hour, depending on what kind of instance I am taking. And I can run my software on top of it and maybe deploy my service over there rather than taking the service as a rather taking SaaS, software as a service. So I might reduce some cost in that cases. And the third terminology that you mentioned was, I think, PASS. I'm not 100% aware about that.
PaaS, platform as a service. I don't know if it's interchangeably
Oh,
used as SaaS or SaaS is a broader term, but
yes,
we do
SaaS could be like a smaller uh, product of, like, yeah, platform as a service. So let's say I want an entire uh, platform, and I'm thinking of example which I can give which would be understandable by others as well. So I want to create, let's say, a data analytics dashboard for business users. So if I have a small startup, let's say 20-30 people's, my requirements are very less, and I can create on-prem software or have Excel sheets to just visualize my data. But let's say if I scale up further and I have a humongous team, 10,000 to 20,000 employees, doing it over Excel sheet is not scalable. However, we still use it. It's not that we don't use it, but we have better reporting mechanisms which can analyze this data, or high amount of data as well as high frequency of data which is coming in regularly. So this is basically a platform, a data visualization platform that I can partnership with. I can give some amount of money and say, hey, the, you are hosting this platform on your end. This will be taken care of business visualization for us, and we won't be maintaining the instances that are running on your end. We won't be maintaining the software on your end, but we will be maintaining our services and the data that is consumed by this platform. And there are more legal agreements which could be on top of it, that you cannot use this data or you cannot use performance based data based on this. Let's say if I want to take chat gpt subscription at an enterprise level, that will become platform as a service, or maybe like a software as a service. I'm not sure where would I categorize it. Maybe I would categorize it as like platform as a service, where my whole enterprise has now chat gpt access or zoom access to do video calls. So that is what pass becomes, I suppose. Yeah.
Thank you, Anurag. I think that was very insightful. Any more questions, Lorene? Any feedback? Any more comments to make? Or we just wrap up our first lecture, which was uh, not surprising, but as surprising enough, quite insightful and amazing. And it's very interesting just to mention me being running Flow, which involves this video conferencing. For me, as a founder and entrepreneur, to be insured the servers that we are running for this video conferencing and meeting, like, once we were calculating the cost, and it turns down to be like all these high performance terminologies and things that we were talking about in this lectures, how many peoples are available on this call, how many are putting up their video on, or how many are sharing those screens, and let's say 500 MB for the upload, 500 MB for the download. So each person, the it was coming around like n into n minus one, like as per the certain variations or variables involved. So, and ultimately, like, this is computing, but at the end it's handling scale, it's handling people, it's handling these learning experiences, and ultimately it's handling cost and revenue. So I find it highly relevant, and I'm looking forward to be able to deep dive in this interesting course and learn from things that I don't know from an interesting set of peers that I am able to find over here. So thank you guys for this first lecture. Thank you, Larine, for arranging it. Thank you, Anurag, for taking this head on for the beginners course and the lecture on it. And thank you for the other participants who we have over here. And looking forward to how we gonna learn, what we gonna challenge ourselves, and making this a successful experience to learn together. So thank you, everyone.
Thank you.
Thanks.